This program is brought to you by Stanford University.
I'm going to talk about converting carbon dioxide into minerals that can then be used in a beneficial way in the built environment. And the basic idea is that most of the carbon in the planet, by a long shot, is in carbonate minerals. 10% of the Earth's crust is limestone, which is all carbonate, and most of the bottom of the ocean is got calcium carbonate ooze in it. And so far and away, the largest reservoir of carbon on the planet, much more so than the atmosphere, the biosphere, anywhere else, is in limestone and different forms of carbonate rocks. And so the general concept we're going to talk about is taking carbon dioxide, and I'm just really going to focus on coal, from the burning of coal, and transforming it into carbonate minerals that are actually used in a beneficial and profitable way in the built environment. And I'm focusing on the built environment because if we're going to really address 20 billion tons of carbon dioxide, we need to do it in a big way. And there are about 12.5 billion tons of concrete poured every year. But when you go into all the aggregate, two-thirds of all natural aggregates are limestone. And just the United States alone consumes about 3 billion tons of aggregate a year, and only 500 million of those tons are used in concrete. A lot of it's used in asphalt. Asphalt's about 90% or so aggregate, and a lot of other places. On a worldwide basis, if you made aggregate out of all the CO2, you could sequester over 50 billion tons of CO2 a year for centuries to come just by putting it in aggregate in the form of carbonates. And also, the other concept is, what I'm going to talk about is doing it in a way that someone's actually going to do it. It's not a tax, it's not a levying fee or something you have to buy, a rich nation buys from a poor nation or anything like that. It's something that people would do anyway. There's actually an aggregate shortage here in Northern California. We import 60% of our aggregate from British Columbia. They mine it up in British Columbia and barge it down here. When we talk about the built environment, we're talking about the main thing mankind leaves behind and the quantities of material that actually need to be taken care of to address the carbon issues. But I'd like to just start off with one little point from my own research here with some of my collaborators at Stanford. I'm a specialist on corals. And corals are the group of anthozoans. By this I mean stony corals or reef-building corals that are responsible for massive structures like atolls, which sequester millions and millions and millions of tons of CO2 from the ocean in hundreds and hundreds and thousands of cubic kilometers of limestone that they form. And for those of you who aren't geologists, 99.9% of all limestone is the skeletal remains of marine organisms that make calcium carbonate and magnesium carbonate skeletons. And again, 10% of the Earth's crust is composed of limestone, and most of the carbon on the planet, by a long shot, is actually sitting in limestone. I'm going to just show you some pictures that I made in 1983 with Nora Garreau, another carbon scientist. We were spawning larval corals and studying them in their first days of mineralization. And so if you weren't aware, during the day, corals look like that. They come out at night and feed, like in the previous photo. And one thing you'll notice is their tissue is green, because it's chock full of symbiotic dinoflagellates that are photosynthesizing, and they have a symbiosis going with the corals, and there are a lot of interesting interactions, but one of them is that the coral when the plants photosynthesize, they take CO2 out of the local system. And that makes it very easy for the coral to precipitate this mineral calcium carbonate. And they utilize the CO2 and convert the CO2 into carbonate. So this is a natural process that goes on every day in the oceans. Now, this photo series I'm going to show you was taken in 1982. And the basic structure of the coral skeleton is a aragonite skeleton. Aragonite is the same mineral that pearl is made out of. It's the orthorhombic polymorph of calcium carbonate. And this is the tissue of the coral, which is really sits up on top of what's called an exoskeleton. So we have an endoskeleton, corals have an exoskeleton. It's outside their body. This is a larval coral after 2 days. And they've laid down their first skeleton, and they start making these skeletons right away. And this is in 1983. This is a prominent Caribbean reef framework builder. And so the tissue has been removed, and we're just looking at the calcium carbonate base of the exoskeleton. And this is a 4-micron scale bar, but they're forming these aragonite fiber bundles very rapidly in a supersaturated ocean and growing very fast. This is at 7 days, and the coral's grown quite a bit more. And again, this is the result of sexual reproduction, where a larva forms and it settles and starts forming skeleton and forming these skeletons. Well, what's remarkable is this isn't happening today. You could repeat the same experiment and go back out, do the exact experiment Nora and I did, and you'll have successful sexual reproduction, but there's no skeleton forming. The larva will settle, can't form its skeleton. It's not in every coral species, but it's in the prominent reef framework builders today. So that's important to me as someone who's interested in coral reefs, because the species that form the frameworks of coral reefs are, for all intents and purposes, extinct today, just in the ocean the way it is today. And that's different from 1983. It has to do with ocean acidification and the absorption of CO2 by the ocean. And I'm not going to spend a lot of time on this, but if we look at the saturation of this same mineral, this calcium carbonate mineral in the ocean today, say 100 years ago or so, there was a time when it was really optimally saturated, and it was easy for calcifying marine organisms to make their skeletons. And this is the best projection for what that level will be at the end of this century. I think a lot of people could argue that it's going to hit this level a lot sooner, so it's not surprising, but nowhere in the world's ocean will really be a place where we'll expect corals to reproduce by sexual reproduction. We'll see reefs persist because most of the propagation of corals is through asexual reproduction via fragmentation, and they keep growing. But the whole structure of reefs is going to change. So, I guess one of the points I'm going to point out in the talk is, if you look at the numbers, and I'm not telling anyone here something they don't already know, but unless something is really drastic is done, it's not going to make a difference. And you really have to look at all this in the context of where we are today. There's 500 coal plants just in the United States. There are 52 in development. And I'll show you in a second why coal is so significant. And I'm sure this audience is probably aware of what's happening with coal plants in China and India and all around the world today. But if we look at electrical power generation, coal is a big part of our future, our children's future, and our grandchildren's future, no matter what we do. And, you know, even given the most aggressive efforts to make electricity other ways, isn't going to significantly affect the amount of coal that's being burnt right now, especially when you get outside the United States. And China is a good example of the increase that's expected in the amount of coal that's going to be burned to create electrical power. So it's very important that we keep all these initiatives going as hard as we can, but we also have to be realistic about the fact that coal is going to get burned to create electrical power on a worldwide basis. If we look at the U.S., and we look at U.S. Emissions of CO2, most of it is coming from the generation of electric power. And 80% of those emissions are coming from the burning of coal in the United States. So the important point I wanted to point out is if we address the coal problem, we could address the whole carbon problem. If we address every other problem out there, cement and steel mills and refineries and all that, but we don't address the coal problem, it's not going to make any difference. And when you really look at various models and the challenges we're talking about, if we just address coal on a worldwide basis, we can reach the levels that we're hoping for. That doesn't mean stopping the other efforts. It means you absolutely have to address coal if you're going to do anything about the change of CO2. The approach that we're going to talk about today is to capture the CO2 and convert it to building materials that are beneficial and useful. I'll just tell you a second about my background. Lee mentioned it, but I've worked on cement since the 1980s. A lot of it was developed right here at Stanford. If you go into the OR and, you know, Stuart Goodman or Amy Ladd or Mike Berlin or any of those guys operate on you, you're probably going to get one of my cements. But these are rapid setting cements that would set even under gushing blood and a broken bone with anesthesia fluids on a cold tourniquet day in Norway. They're very high-performance cements, much stronger, much tougher, set faster, worked better than any concrete or Portland cement that you would use in construction today by an order of magnitude. So just to give you a feeling for it, these cements would achieve 10 or 15,000 PSI compressive strength before you even pulled the patient off the table. The sidewalk out here might reach 5,000 PSI after 28 days. So I was over here at the Woods Institute, and I learned that the production of Portland cement was considered the third largest source of anthropogenic CO2, which I should have known, but I didn't know that. You know, when you calcine limestone, it makes sense. It occurred to me that it would be possible to formulate alternatives to Portland cement that use carbonate chemistry instead of silicate chemistry. And the other thing, here at Stanford, we had looked at the Giza pyramid in Egypt, which is about 5,000 years old, and it's actually composed mainly of concrete. We'd all heard stories that the pyramids were built out of stones of nummulitic limestone that were carved with copper tools, and there are a lot of blocks like that in the pyramids, but actually the majority of them are a concrete that is a carbonate-based concrete. We were fooled because the aggregate in the concrete is that same nummulitic limestone that the blocks are cut out of, and they look very similar, but in fact it's a concrete. And it's lasted for 5,000 years very well. So there's other types of alternatives to concrete. The concretes we use today, the Romans came up with, a couple thousand years ago, and we've been working on them for a couple thousand years. But even the Mayan pyramids employ these carbonate-based concretes. And the idea is, let's take CO2 out of the system the same way corals do, form carbonates, formulate them into useful products with beneficial use. And as I said, the volumes are about the right volumes. A yard of concrete has approximately 2 tons of concrete in it. So 12.5 billion tons of concrete, 6 billion yards. The material I'll tell you about has half a ton of CO2 per ton. So we could, if we took all the concrete and we used our process instead of the conventional processes, we could sequester about 6 billion tons of CO2 that way per year. If we used it in aggregate, you can multiply that times 20. And there'd still be need for more aggregate in all the materials. So it's of the order of magnitude that it's a place you could put it and it'd stay there. Carbonate minerals are carbonate CO3, so you're taking CO2 and making CO3. It's a very stable covalent complex. The only way to get the CO2 back out of it is with acid or very high heat. Calera Corporation currently has a plant down at the Moss Landing power plant down there between Monterey and Santa Cruz counties. It's a 1,000 megawatt gas-fired power plant. It's one of the largest power plants on the West Coast. But we moved into an old magnesium hydroxide facility, 200 acres that Henry Kaiser built during World War II to make magnesium hydroxide for the war effort, and then switched over to magnesium oxide kiln bricks. But they were making it by pumping about 60 million gallons of seawater in every day and precipitating the minerals out. And they were making 6 million tons of magnesium hydroxide a year there. And in '99, it went out of business because the Chinese were importing it for cheaper than they could make it for. And it's been sitting fallow. But there's 300,000 square feet of covered area. We've got 7 3 million gallon reactor tanks, a permit to discharge 60 million gallons of water, and a power plant next door that puts out 4.2 million tons of CO2 every year. But the process is that we take flue gas, and this is something I want to talk about in more detail. The flue gas from a gas-fired power plant has only got a couple percent CO2 in it. Flue gas from a coal-fired plant has 10 to 15% CO2 in it. Most of the talk you've heard about sequestering and transporting CO2 is talking about emissions from refineries that have on the order of 95 to 100% CO2. And those technologies don't apply to coal-fired emissions. They don't apply to gas-fired emissions. But we interact it with the seawater out of Monterey Bay. We precipitate calcium and magnesium carbonates and make building materials out of it. The one byproduct is fresher water because we take calcium and magnesium out of the water, which is typically referred to as hardness. So we essentially soften the water. And after water is softened and those ions are gone, it's about 60% less energy intensive to then put through a reverse osmosis membrane for desalination. So there we have a contract with the Pajaro Sunny Mesa Water District for a certain number of acre feet of water per year that we're putting in a desalination plant down there. Monterey's got some real water problems. But we're not doing anything any different than natural biomineralization of carbonate. There's no special chemicals or anything. You know, you had this in high school chemistry, but CO2 plus water makes carbonic acid, and it can be disassociated to bicarbonate and then to carbonate. And when it's in the carbonate ion form and you have magnesium and calcium, you form calcium and magnesium carbonates. Now, it's complicated. There are dozens of different polymorphs of calcium carbonate and magnesium carbonate, and they all form things. You couldn't just take this stuff and say, great, I've got some cement. It doesn't work quite that way. But this is the basic chemistry. By polymorph, I mean, if you take diamond and graphite, those are both just pure carbon, right? But they have very different crystal structures. Same here. There are many different crystal structures in the carbonate system. We take that slurry, and we're forming two products. One is cement, and we make this cement by pumping the material, which starts out looking like milk, and it's dewatered, and then it looks like plain yogurt, and it gets pumped into a spray dryer, which is a technology that's used to make powdered milk. And the energy to run the spray dryer, because it still takes 900 and something BTUs per gallon to evaporate water, is coming from the waste heat of the power plant. The power plant's putting out enormous amounts of gas at over 300 degrees Fahrenheit, and there's plenty of heat that's just being wasted to run through a heat exchanger and run the spray dryer. We also have an accelerated lithification process, which lithification is how geologists discuss rocks getting hard to make limestone, synthetic limestone, which, as I mentioned earlier, 2/3 of all natural aggregates are limestone anyway. The main reason for that is limestones are stable at high pH, and Portland cement has a very high pH, 13 to 14. And if you put a silicious rock like a chert in it, it will react and make it weak. This is the Moss Landing plant, and this is our property here, and this is Dynergy's property. This is the power plant, and the whole enchilada is right there, and Mbari is right out there. You might notice we have 40 acres of white stuff. That's magnesium hydroxide, which had accumulated since World War II, that had gotten through the filter presses that was too fine to do anything with, and so it's there in a pond. So one of our things we use is base in our process. So this site we have 5 million tons, and we actually reuse a lot of waste materials in our processes. We're establishing at a coal plant on the East Coast now, and there we're using actually fly ash, which is the most common waste material in the world that also has a lot of value. So in our cements currently that we're making, we're also consuming not just seawater and flue gas, but magnesium hydroxide. And our hope is to return Mohokoho Lagoon here to an estuary when that's fully mitigated. We're less than a year and a half old as a company, but we've moved pretty fast. We've got 65 employees. We've got another 20 down at Moss Landing. We've got 20,000 square foot of labs. But we're at a pilot stage where we're making 1 ton a day right now, and we're getting a demo plant prepared that's going to take a flue gas stream of up to 80 megawatts of a slipstream from the gases of a coal-fired power plant. And we've got actually over a dozen candidates, and we're trying to decide how many of these we can do at once. At the commercial scale, most coal plants are about 500 megawatts and up to 1,000 megawatts. The Indians are building one that's almost 3,000 megawatts right now. And in our technology, we're capturing currently in the 80 to 85% range of the CO2 when it goes through. And we have some new technology that's going to exceed 90%. So we're really pretty much cleaning up that flue gas stream pretty effectively. The key performance indicators are how many tons of CO2 are we able to make, how many tons of cement from those tons of CO2, the capital costs and the operating costs, and the parasitic load on the plant. And there's something real different from what we're doing. There's a lot of people interested in taking CO2 from flue gas streams, but when they're done, they have CO2. When we're done, we have minerals, carbonate minerals. When you have CO2, you then have to do something with the CO2. So the conventional approach, and conventional isn't the proper term because it's really a new approach, is called CCS, or carbon capture and sequestration. It's a very expensive process. We actually aren't separating CO2 in our process. We're just converting it to carbonate. Part of the expense and the high carbon footprint of conventional CCS is all the equipment and the compression and all the handling of the gases, having to transport it. You know, I mean, everyone's aware of the city of people who got killed in Africa when a big cloud of CO2 came out and killed everybody. The state of Florida won't even let you do this. It's tough. And then the idea is to inject it into a stable place in the ground where it will stay there. And there are costs associated with all of that. You know, and the hope is that it'll stay. And there's probably a whole bunch of places around the world where it will stay, and there's probably a whole bunch of places where it won't stay. And it's going to take years to understand this. But you know, what we're doing at this point is making something we're planning to sell. And I think that's going to be important. I don't believe the Chinese or the Indians are going to do it unless it's economically feasible, regardless of the regulation. But that's a side point. To do the other conventional methods, you have to remove what are called criteria pollutants ahead of time. And these are the sulfur and nitrogen compounds mainly. The process we're using actually traps those as a consequence, a fortuitous consequence of what we're doing. The parasitic load, meaning the amount of power from the power plant it takes to do what we're doing, is insignificant compared to the conventional processes. But more importantly, when you're done with the conventional CCS idea, if they're ever scalable at all, you're still just stuck with liquid CO2. And you have to figure out what to do with that. So this is where we're heading. But I want to emphasize this point because it's such a common misperception. We've been having a lot of interaction with people in Washington who've been getting this stimulus package passed. And see, we know a whole lot about enhanced oil recovery and carbon capture and sequestration from flue gas coming from refineries. And, you know, if I'm Exxon, the problem's solved, right? Because for decades, I've been taking this stuff, which is mostly CO2, and injecting it into old oil reservoirs and getting 5 barrels of oil for every ton of CO2 I pump down there. You know, I mean, that's a no-brainer. But if you go talk to Larry Kellerman, the CEO of Cogentrix, or David Crane, the CEO of NRG, or the guy from Duke, you know, Jim Rogers, or the head of Dynergy, or any of the people we're dealing with, they're not even considering CCS. Not even considering it. Because the cost to actually separate CO2 from these dilute streams of gas that are being produced by coal-fired power plants is just a non-starter. It's not only is it too expensive, but the amount of CO2 you're putting out just doing it makes the whole thing a non-starter. And that's before you even think about finding a place in the earth where you can inject it. So it's important to remember CCS might end up being a great technology, but it only applies to what's coming out of you know, very pure CO2 streams. You're not going to take CO2 from most coal plants without a lot of different types of processing and inject it in the ground. So there's really not an answer. And if you don't believe me, just ask yourself, how come none of the largest power providers in the world are pursuing it? It's because they get to that separation step and it's a standstill at that point. But there are a number of approaches being taken, and there are progressively more stringent environmental regulations, not just for CO2, but for all the other criteria pollutants as well. And as I mentioned, they go together. If you're going to actually try and separate CO2, you have to separate the criteria pollutants first. What I mean by criteria pollutants are these are the pollutants that are covered by the Clean Air Act. CO2 is not under the Clean Air Act right now. And this would be a typical setup. You're burning coal. You have a NOx scrubber for the nitrogen compounds. There might be a bag house where you're taking out the fly ash. And then you get around to the sulfur compounds. And that's before you start the CO2 removal to sequester it. And all of this stuff has quite a bit of cost and CO2 footprint associated with it. And so if you own a coal-fired power plant and you're looking at CO2 sequestration, you're also looking at all this other stuff too. And most of the power plants in the world don't have these back-end scrubbers. And actually, only about half the power plants in the US have them at this point. So if I'm a power plant right now and I'm looking at a large capital outlay just to take care of these guys, and now they're telling me I need to also add CO2 in there, I'm a little confused because I don't know how I can continue to run the power plant if that's how it's going to happen. The options, the main options available to them, state-of-the-art, would be an amine process that is being commercial at a very small scale at this point, and has a significant parasitic load and a large capital expenditure for the power plant, and a chilled ammonia process. And we're talking very large amounts of ammonia that you're bringing in. And having just gone through the California Coastal Commission, I'm trying to even imagine my partner down in Moss Landing, Dynergy, talking about bringing that much ammonia into Monterey County, into the Monterey Bay Marine Sanctuary. It's a complete non-starter. So if you're up on Capitol Hill and you're trying to legislate, and you've got the CEOs of all the major power companies coming in and saying, look, this isn't going to work. It's a non-starter. Here are all the reasons it's not going to work. And a hydrologist comes into your office and says, look, I've got the carbon problem. We're going to take all the CO2 from power plants and inject it into the ground. What do you think that senator, how do you think that they're going to respond in the stimulus bill? And as a result, the stimulus bill probably has not just 10 or 20 billion, but probably 50 to 100 billion less money in it for the kinds of things to mitigate carbon that there could have been, had there been a credible scientific presentation made to the people voting on it. But in these post-combustion technologies, there are a lot of issues that need to be taken into consideration in implementing these. Now, the initial impetus for this project was just the carbon footprint of Portland cement, which is simply the fact that when you heat limestone, and you all are probably familiar, there's a big quarry down in Cupertino. If you're driving down Highway 85, you look up on the hill. That happens to be the Calera limestone, by the way. They're quarrying Calera limestone, and they make about 1.4 million tons of Portland cement there every year, and it puts about 1.4 million tons of CO2 into the atmosphere. So the initial idea is, well, if we come up with a replacement for Portland cement, we could offset the carbon footprint from Portland cement. And if you look at it, most of the Portland cement is being poured in, actually, China. 47% of the concrete poured last year was poured in China. But it's growing very fast, and as the developing world develops, concrete is the most used material just behind water. So if the concrete stops, everything comes to a standstill. There are no building projects or anything. And even here in California, they talk about the concrete shortage of '82. Like they'd been through the war, and they had. What we're seeing in the market today is, in the U.S., there's about 120 million metric tons of Portland cement used, 2.5 billion worldwide. There are also a big trend now is called supplementary cementitious materials. And to give you a feeling for it, the idea is if you can replace the cement with a filler and have it still get strong, it won't have the same carbon footprint. So in the Bay Bridge, Caltrans specified a 50% fly ash blend. So the Portland cement in the span of the Bay Bridge going from Treasure Island to Oakland, the cement there is actually only 50% cement, with the idea being that it's going to cut the carbon footprint of the cement. I'll talk more about this. Of course, they used fly ash, and the fly ash was barged in from China because we don't have any fly ash because we don't burn coal in California. But the thought was there. But it's like a lot of green themes. They're not really that green. And then there's quite a bit of aggregate, about 30 billion tons of aggregate used every year. And if you look at it from a business point of view, cement sells for about $100 a ton, aggregate's a lot less, and there are other products, but there are a lot of beneficial areas to use these materials. Just like the power companies, cement companies are regulated, not just for the criteria pollutants, and CMEX, which is one of the largest ready-mix companies and the second largest cement company, just got a big fine. They're all coming to us asking us about mitigating their pollution and then combining our efforts in distribution. And so sustainability is a big issue in the construction industry and the concrete industry, and you've probably heard of green building and LEED and all that kind of stuff. The main approach that is being looked at is what are called supplementary cementitious materials. And right now in the state of California, Caltrans specifies 20% supplementary cementitious materials in all their projects, and they're trying to get it higher. There's actually a shortage of fly ash, which is the main one, and blast furnace slag is the other one. And the reason there's a shortage of fly ash, well, in the West, is because we don't burn coal, but is the EPA is coming down on the mercury regulations, and so there's more fly ash which is unusable because it has high carbon in it, which has to do with retaining the mercury. So there's a shortage of these supplementary cementitious materials anyway. But even if we substitute 50% all the Portland cement with fly ash, that would only result in a 2.5% reduction of CO2 worldwide. For the cement industry, one option is to do carbon capture and sequestration, and a number of them have tried chilled amine processes and aren't going forward with them. But however they look at it, and I'm repeating this from the CEO of every major cement company that we met with, and these are some of the largest companies in the world, they feel it would add about $50 a ton to the price of cement. And they couldn't operate under those circumstances. And there's other guidelines like LEED, for example, but LEED doesn't even consider CO2 as something important. You can get a point for a bike rack, but you can't get anything for sequestering CO2, although that's going to change. But here are the materials that I'm going to talk about that we're making. We're making a carbonate supplementary cementitious material. Caltrans will be testing this in their labs and hopefully putting it into the spec. We're making a synthetic aggregate, basically synthetic limestone, and fine aggregates in the form of sand, which I'll talk about in a second, and coarse aggregates in the form of pebbles and gravel. And we're also making a material called the pozzolan, which is named after the city of Pozzolana near Mount Vesuvius, where the Romans put the first fly ash and limestone together and sintered it to make the first Roman cements. Pozzolans are if you're building a very high skyscraper and you need very high strength cement, you would add a pozzolan, which has a lot of amorphous silica in it and dissolves in the high pH of the cement and gives you coherent grain boundaries and lowers the permeability and gives you very high strength. And at the locations where we're mitigating fly ash in addition to making cement, we incorporate that into the cement and it makes a great cementing material. The supplementary cementitious materials just look like cement. The Calera one is white, so when it's combined into Portland cement, which is gray, it gets sort of milky in color. And the way they work is you put them into the cement matrix, and it's a way to increase the strength and durability in addition to lowering the carbon footprint. So here are some blends of ordinary Portland cement that have the supplementary cementitious material in them, and they look pretty similar on a microstructural basis, and grow in and strengthen the footprint, the matrix. Now we just made a presentation to the largest concrete gathering in the world. And we've introduced the concept to the concrete world of a way to calculate the carbon footprint of a yard of concrete. So this is something quantitative, and I think it's going to be important. And we just heard today that one of the important certifying bodies has adopted this. But basically, if you order a yard of concrete, or when they're building these buildings at Stanford, they order 10,000 yards of concrete, there's a carbon footprint associated with that yard of concrete. And this is a simple calculation. We take the amount of CO2 embodied in each ingredient, and this is in pounds and yards, I apologize, times the mass, and we come up with a carbon footprint of each ingredient. So transportation is a big aspect of the carbon footprint of these heavy materials, as you can imagine. So for Portland cement, the Portland Cement Association says the average ton of Portland cement only generates 0.86 tons of CO2. We'll take their number. And then when they transport it, there's some CO2 associated with that. So we come up with a number of 876 kilograms of CO2 associated with that Portland cement. For the fine aggregate or sand, or the coarse aggregate or gravel or pebbles, we're assuming no carbon footprint. There's probably some associated with the mining and quarrying, but it's probably de minimis. Here, there's a carbon footprint with transportation. Since fly ash is used so commonly, we've associated no carbon footprint with that, but a large transportation, because fly ash has to be transported very large distances. And then the water itself has a small carbon footprint associated with it. And then we take the Calera materials. The supplementary cementitious material has half a ton of CO2 in it from the power plant for every ton. We're assuming some carbon footprint associated with transportation. We get negative 0.45 tons. So it's a carbon negative material. And that's true with the sand and the coarse aggregate as well. Now here's a typical yard of Portland cement, of concrete that uses Portland cement. And if you take the cement, the water, the sand, and the gravel, you've got about 500 pounds of CO2 associated with that yard of Portland cement. And that's sort of a graphic description of that. If you take the span of the Bay Bridge, which used a 50% fly ash blend, so there's a little less Portland cement, and there's some fly ash in there, in addition to the coarse aggregate and the fine aggregate in the water. And that gets it down to 300 pounds of CO2 per yard. And that's a histogram of that. Now we start using the Calera materials. And in this case, of the cementing portion of the concrete mix, and remember, the cement is only 20% of the concrete. The other 80% is aggregate. Of the cementing portion of this yard of concrete, 60% of it is Portland cement, 20% of it is Calera cement, 20% of it is fly ash. And it's about the same. But the difference is that fly ash is very hard to work with, and it takes much longer to set. And you have to leave the forms on like a whole week longer, and it has a huge impact on construction costs. So if I'm a contractor, I'd much rather have this mix, because this sets just fine and it handles nicely because of the Calera material. And this is a graphic description of that. But the idea is it's not good enough to just be less bad. The idea is our idea is to sequester the carbon in the built environment here. So here's a carbon neutral mix. We take Portland cement, water, sand. But we also, in addition to the 20-20-60 blend of the cement, we replace a lot of the sand, not all of the sand, but a fair amount of the sand, 50-50, with our sand. And by replacing it with our sand, we get to a carbon neutral concrete. And that's what that looks like. Here's another carbon neutral concrete. In the Portland Cement Association like this, we don't take the Portland cement away at all. All we do is use quite a bit of our sand compared to the regular sand. And, you know, I think that I was like, the funnest thing right now is, did you know there's a sand shortage in the Middle East? So we're talking to a big carbon neutral city near Abu Dhabi right now, and I was shocked to learn that they barge in all their sand. It's because there's so much salt in the sand, and salt corrodes rebar, and you can't do that, and there's no fresh water to wash it. But you know, so I'm excited about making sand and selling it to the Middle East, and we're not going to embargo or price fix or anything, but you know, we'll be their sand supplier. This is a carbon negative mix. And I want to stress, these are all mixes that the average worker out on the job wouldn't know was not regular concrete. You know, we can go much more radical than this and make some very high performance things that are really different. These are baby steps. But here we've still got a lot of Portland cement, water, fly ash. But we're using Calera cement, Calera sand, and Calera gravel. And here it's negative 1,000 pounds of CO2 per yard. So this is a good place to put CO2. It's going to be in the road, it's going to be in the sidewalk, it's going to be in big dams, it's going to stay there. It's essentially the same as the White Cliffs of Dover. And that's not even accounting for the offset of the cement itself. The testing we do is, the tests themselves are designed by the ASTM C1157, which is the construction grade concrete test. And then the American Concrete Institute actually sets the code. So Palo Alto uses this, and it's uniformly harmonized on a worldwide basis in terms of the standards that we have to test. We have several scientific teams. One is a materials development team, and it's headed by the past president of the American Concrete Institute, who's one of the most respected people in the whole concrete industry. We just, as I mentioned, gave a presentation at the World of Concrete, which usually has about 80,000 attendees. It was a little down this year, about 60,000 attendees. And everybody's on the program. You know, the cement companies are on the program, the ready-mix companies are on the program, the aggregate companies are on the program, the admixture companies are really on the program because they want to be the first to design an admixture that works, you know, custom with, be like a software developer for some new hardware or something like that. So this was a very positive product launch for us. And we also did give this 90-minute presentation, and it was given by myself and the past president of the American Concrete Institute, and all the people that came got AIA accreditation for learning how to calculate the carbon footprint of a yard of concrete. Well, there are over 1,000 cement plants around the world, and there are more and more going in all the time, especially in the developing world, opening up limestone mines, burning coal mainly, and other things, to develop the most used, other than water, material that mankind uses. Concrete is the most used building material there is. So there's a possibility, although it's not our first focus, that this technology could be matched up with the cement plants too. People say, are you going to replace Portland cement? The cement market is growing so fast, no one's going to replace cement. In the developing world, people are needing to pour concrete at an alarming rate. And every time they put another ring of a city around Beijing, it's all that concrete, and then they have to build more power plants, and they keep going, because the main use of electricity is to light buildings and heat them. So they go hand in hand. But there are almost 5,000 power plants, and the future is that there's going to be more and more coal plants and burning coal around the world. We see this as a really urgent problem that needs to be addressed in a big way with a real solution that can be implemented really fast. And we already have letters from all the major distributors of these building materials saying not only would they be happy to distribute these products, but they'd be enthusiastic about distributing these products, which helps us out a lot and is very supportive of what we're doing. So I think my time's up, so I'm going to call it quits. Yeah.
About 5 minutes for some questions.
Yeah.
Does your process work without seawater? If you're inland, how do you get magnesium and calcium that you require?
Yeah, that's a really good question, and it's the most frequently asked question, so I appreciate you asking that. So seawater's got about 400 parts per million calcium and about 1,200 parts per million magnesium. And that's pretty good, and what's nice about it is it's consistent, for the most part, all around the world. And that's a nice way to start out. But when you get into the plant economics, one of the large drivers is actually pumping water. And so if you can increase the yield by having a higher concentration, you can reduce the amount of water you have to pump. And there are other reasons. So, and of course, as you mentioned, there are a lot of inland plants that aren't near seawater anyway. Almost all sedimentary basins all over the world are full of ancient seawater, massive amounts of it. Most guys that drill for oil hit brine, right? They don't hit oil. So we've poked into brine reservoirs all over, and it's almost unlimited. And the average brine concentration is about 39,000 parts per million calcium. So it's literally 100 times higher than seawater. It means you have to pump 100 times less water, which has a huge impact on the footprint and the energy to pump and a lot of other things. I mentioned we're mitigating fly ash at Indian River in Delaware. There, the fly ash is full of calcium oxide, magnesium oxide, and all those things. And there's many, many other minerals that, if the technology is worked out to dissolve them fairly quickly, we're just looking for divalent cations to go with the carbonate. Yeah.
You mentioned in the beginning about carbonate cements.
Yeah.
Do you see replacing the Portland cement as well with aggregates?
Yeah, we have those in the lab now, but you need to understand how conservative this industry is. I came out of orthopedics, and I thought that was pretty conservative, and it is. And the FDA is pretty conservative, and it took a decade to get my first cement, where I wanted it to be. But if you're building bridges, it's a bad day, if a bridge falls down, and they're very, very conservative. So just to give you an example how slow it moves, in Europe, they use about 30% ground limestone as a filler in the cement to offset the footprint. In the United States, they've been working on it for almost 20 years, and Caltrans just adopted 5% replacement of limestone. So I'm sure we'll go there, and we're going to run out of limestone quarries, or people are not going to permit them, and all that. But we've already got cements that are very exciting. Yeah.
Now, in an optimistic vision about how well it might work, how long is it going to take to scale up to be able to deal with tens of % of the world's CO2 emissions? And how much would that cost?
Yeah. Well, what's nice about it is because it's we're going out as a profit center for these places, even though they're very cognizant of regulation and the power industry would like to just know what the rules are. Because of that, if we can go out, our problem right now is we have too many power plants that want to work with this technology, but we've implemented it. And I really get back to the management team that we've put together to implement this, and we're having a lot of interaction or support from foreign governments that are very interested in funding this and replicating it. So I think it can spread faster than most solutions, but the main reason is if we just implement the carbon legislation in a strong way where people, and it's mandatory and it has to happen fast. If you're an owner of a power plant, then you've got to get these other pollutants controlled too, that what are called the criteria pollutants. So these power plants are today looking at an average plant $500 million to $1 billion investment just for the criteria pollutants before they even get to the CO2. And our average plant is looking on the order of about $250 million. So getting that capital compared to what they would have had to have done is actually a much faster route for them to get the whole project financed and move forward. But that's the key, is how fast we can implement. And we've been able to attract an incredible group of people that have left incredible jobs to come join Calera. Our head of operations left NRG, which is the largest non-regulated power company, where he oversaw all their plants, to come do this at Calera. He brought his vice president of plant construction, who's built power plants all over. We're going to be in Australia in a couple of weeks, because they want us to. They're going to fund plants for us down there, and these guys built and managed half the plants that we're going to look at. We've got the head of GE's emission control technology who left to come and join us and work on this, and the most famous guy in the concrete industry is our head of material development. So we've been able to get the kind of team together, and there are many other people I could mention that can really implement this. But that's the key question, is to really get to that 12 billion tons, we have to move fast and we have to move in parallel. Yeah.
How will the price affect the owner of the building or the contractor? And how can you get to a price point where it'll pull, where the owner is going to want to do it? I'm a concrete contractor, and today's world is vastly different than it was a year ago, or 2 years ago. And all my owners care about now, they're immediately pretty much dismissive.
Right.
A whole lot they thought about a year ago.
I think, from your ready-mix plant's point of view, this shouldn't be too much different cost-wise or procedurally even to just putting fly ash in the mix as a supplementary cementitious material. And as part of the sand blend, it should have zero visibility. The prices we're planning on are not inconsistent with, the current prices they're paying.
We can save the owner $5 a yard, he's going to go, if it's 5 extra.
Now, believe me, I'm fully aware. We built a model where we actually give the material away. And in Kyoto countries, that's actually a much more profitable model because the usage goes way up when it's free. And we base the revenue model on the credit. So we've got a lot of interesting ways to go and make it happen.
We've hit our time limit, so we could all thank Brent for being here.